Rain began across Tampa at 4:47 a.m. on a Tuesday in late September, arriving as a broad system moving inland from the Gulf of Mexico with no tropical designation and no forecasted severity beyond moderate precipitation. Initial accumulation rates measured between 0.8 and 1.2 inches per hour across most of Hillsborough County, well within the design capacity of the municipal stormwater system, which had been engineered to handle short-duration events of up to 2.5 inches per hour for periods not exceeding 3 hours. The storm drains along Dale Mabry Highway, Bayshore Boulevard, and the grid of streets radiating from downtown accepted flow as designed, channeling runoff into underground pipes ranging from 24 to 72 inches in diameter, which in turn fed into retention ponds, lift stations, and gravity-fed outfalls leading to Tampa Bay, the Hillsborough River, and McKay Bay. Surface water disappeared from pavement within minutes in most areas, and early morning commuters encountered wet roads but no standing water. The system operated within its normal envelope. Rainfall continued without pause, and by 6:15 a.m., cumulative totals across the city had reached 1.4 inches, with rates holding steady rather than tapering as morning progressed. Weather radar showed the system extending across the entire width of the peninsula, moving eastward at approximately 4 miles per hour, which meant continued precipitation over Tampa for an extended duration, rather than the typical brief passage of a storm cell. By 7:30 a.m., rainfall totals had reached 2.8 inches across central Tampa and 3.1 inches in neighborhoods south of Gandy Boulevard, and the first signs of reduced drainage efficiency appeared in areas where stormwater infrastructure relied on pump stations rather than gravity flow. The Ballast Point area, situated at elevations between 6 and 9 feet above mean sea level, depended on 3 lift stations to move accumulated water upward into discharge pipes leading to Old Tampa Bay. Each station had been designed to pump at a combined rate of 12,000 gallons per minute under normal operating conditions, but influent flow from the surrounding 340-acre drainage basin had reached 14,500 gallons per minute and was not declining. Pumps ran continuously rather than cycling on and off, and water levels in the wet wells began to rise incrementally, reaching thresholds that would normally trigger only during the heaviest portions of a storm rather than being sustained over hours. Similar conditions developed at lift stations in Palma Seca, parts of Hyde Park, and sections of South Tampa where natural drainage to the bay had been constrained by development and roadway construction. The pumps did not fail, they operated at rated capacity, but inflow exceeded outflow by margins that, while small in any given minute, compounded over time. Rain continued at rates between 0.9 and 1.1 inches per hour, and by 8 a.m., citywide accumulation had reached 3.5 inches with no indication of a break in the weather pattern. Retention ponds throughout the city, designed to temporarily hold runoff and release it gradually through control structures, began filling beyond their normal operational ranges between 8:15 and 9 a.m. A pond serving a 220-acre residential area in Carrollwood, engineered with a maximum capacity of 8.2 acre-feet and a typical depth of 4 feet during dry conditions, reached a depth of 6.8 feet by 8:45 a.m. The control structure at the pond's outlet, a concrete weir with an 18-inch pipe leading to a downstream drainage channel, discharged at its maximum rate of approximately 95 cubic feet per second. But this rate had been calculated based on the assumption that inflow would diminish as the storm passed, allowing the pond to drain over a period of 12 to 18 hours following the event. Inflow had not diminished. The pond continued to receive runoff from streets, parking lots, and rooftops at rates that kept water levels rising rather than stabilizing. Similar patterns emerged at retention systems across Temple Terrace, Town and Country, and neighborhoods east of the University of South Florida. None of the ponds overtopped their banks, none breached their perimeters, but each approached the upper limits of its design envelope while rainfall continued, leaving no capacity margin for any additional influx and no mechanism to accelerate drainage beyond the fixed discharge rates determined by outlet pipe dimensions and elevation differentials. By 9:20 a.m., rainfall totals had surpassed 4.2 inches, and the storm system showed no signs of dissipation. Standing water appeared on roadways in low-lying areas, not because drainage inlets had become blocked, but because the systems receiving flow from those inlets had reached capacity and could accept no additional volume. Along sections of Hillsborough Avenue between Dale Mabry and Armenia, water accumulated in the roadway's center and right lanes to depths ranging from 2 to 4 inches, not flowing toward curb inlets but instead pooling in place as water already in the drainage pipes prevented new inflow. A 4-block section of North Boulevard near the Seminole Heights neighborhood retained water depths of 3 to 5 inches across the full width of the street, despite functional storm drains spaced at standard intervals of 300 feet. The subsurface pipes, ranging from 30 to 48 inches in diameter, remained full, carrying flow toward a trunk line that itself was operating at capacity, creating back pressure that prevented additional water from entering the system. Traffic moved through these areas at reduced speeds, and some vehicles chose alternate routes, but no streets were closed and no emergency notifications were issued. The condition was not blockage, but saturation of capacity. Water continued to fall at rates near 1 inch per hour, and by 10 a.m., accumulations had reached 5.1 inches across most of the city. Soil in landscaped areas, parks, and undeveloped parcels had absorbed precipitation during the early hours of the storm, but saturation had been reached, and additional rainfall now contributed directly to surface runoff rather than percolating into the ground. Between 10:30 a.m. and 12 p.m., the storm's intensity decreased slightly, with rainfall rates dropping to between 0.6 and 0.8 inches per hour. But this reduction did not translate into improved drainage conditions because the accumulated volume already within the stormwater system could not be evacuated quickly enough to restore normal capacity. Pump stations that had been running continuously for more than 5 hours showed no decrease in wet well levels despite the reduced inflow rate because discharge capacity remained constant and could not be increased beyond design limits. The lift station serving the Virginia Park neighborhood, equipped with 2 pumps each rated at 3,500 gallons per minute, continued to operate both units in tandem, but water levels in the collection basin remained at 87% of maximum depth rather than declining. Retention ponds that had filled during the morning remained near capacity, discharging through their control structures at maximum rates, but unable to lower their water levels measurably over the midday hours. A pond in the West Chase area, serving 410 acres of residential and commercial development, held 14.7 acre-feet of water against a design maximum of 16.0 acre-feet, draining at approximately 120 cubic feet per second through a 24-inch outlet pipe. But this discharge rate would require more than 9 hours to return the pond to its normal operational level, and rainfall had not yet stopped. By 12:30 p.m., total accumulation exceeded 6.0 inches across Tampa, and streets in South Tampa, parts of Town and Country, and sections of East Tampa retained standing water that had been present since mid-morning. The storm system finally moved off the Florida peninsula around 1:45 p.m., and rainfall ceased across Tampa by 2:10 p.m., leaving a total accumulation of 6.4 inches measured at Tampa International Airport, and amounts ranging from 5.8 to 7.1 inches at rain gauges distributed across the city. The cessation of rainfall did not immediately restore normal conditions. Standing water remained on dozens of street segments, in parking lots, and in low areas of residential yards and parks. The drainage system, now receiving no new inflow, began the process of evacuating the accumulated volume, but this process proceeded at rates determined by fixed infrastructure capacities rather than any accelerated emergency response. Pumps at lift stations continued to run, moving water from collection basins into discharge lines, but the pumps could not operate faster than their rated capacities, and wet well levels decreased slowly, dropping by increments of 1 to 2 feet per hour. Retention ponds drained through their outlet structures at the same rates they had maintained during the storm, and water levels receded by small fractions of a foot each hour rather than emptying rapidly. The system functioned as designed for post-storm drainage, but the duration required to return to normal state extended well beyond the few hours that typically followed afternoon thunderstorms. Streets that had been covered with 3 inches of water at 2 p.m. remained wet at 4 p.m., with depths reduced to 1 or 2 inches, but not yet fully cleared. By early evening, most major roadways had returned to normal conditions, but numerous residential streets, parking areas, and low sections of parks retained standing water or saturated ground surfaces. The drainage system's behavior during the event had not included any component failures, blockages, or mechanical breakdowns.
Every pump that had been operational before the storm remained operational afterward. Every pipe that had carried flow during the event continued to carry flow. Every retention pond that had been designed to temporarily hold water did so without structural compromise. What had occurred was a condition in which the duration and consistency of rainfall had exceeded the time-based assumptions embedded in the system's design. Stormwater infrastructure in Tampa had been engineered to handle specific intensities for specific durations, typically using design storms based on historical rainfall data and statistical models that calculated the probability of various precipitation rates occurring over periods of 1 hour, 3 hours, 6 hours, or 24 hours. The storm that had passed over the city did not fit neatly into these categories. It had not been intense enough to qualify as a severe event in terms of inches per hour, but it had been sustained long enough that cumulative volume exceeded what the system could evacuate in real time. The margin between inflow and outflow capacity, which normally remained positive, had inverted for a period of several hours, and the accumulated deficit had taken the remainder of the day to resolve. Municipal stormwater management staff reviewed operational data from the event over the following days, examining pump station logs, flow monitoring records from key trunk lines, and water level readings from retention ponds across the system. The data confirmed that no equipment had malfunctioned and no abnormal conditions had been detected beyond the elevated water levels and extended drainage times. Pump runtime logs showed continuous operation of multiple stations for periods ranging from 7 to 9 hours, which was unusual but not outside the equipment's operational capability. Flow rates in major drainage pipes had remained at or near capacity for sustained periods, but nowhere had pressure exceeded design limits or caused structural concerns. Retention pond levels had peaked between 80 and 95% of maximum capacity at various locations, with none exceeding their design thresholds, though several had remained above 70% capacity for more than 8 hours after rainfall ended. The review noted that the event's total rainfall of 6.4 inches over approximately 9 hours corresponded to a statistical recurrence interval of roughly 10 to 15 years based on historical data, meaning it was not an extreme outlier, but also not a routine occurrence. The stormwater system's design standards, established through engineering guidelines and updated periodically based on regulatory requirements, had been based on the capacity to handle a 25-year storm event for major infrastructure and a 10-year event for residential drainage. But these standards referred to peak intensity over specific short durations rather than sustained moderate rainfall over extended periods. Engineering analysis of the event focused on the relationship between design assumptions and actual performance under conditions that fell between standard design scenarios. The system had not been overwhelmed by intensity, which was the primary metric used in drainage design, but had instead been stressed by duration, which was a secondary consideration in most planning documents. Retention ponds had been sized to hold the volume generated by design storms of specific durations, with the expectation that discharge would begin during the storm and continue until the pond returned to normal levels within 12 to 24 hours. The extended nature of the September storm had meant that ponds filled without the anticipated opportunity to begin lowering their levels until the rain stopped, and the time required to drain afterwards stretched into the evening and overnight hours. Pump stations had been designed with capacity to handle peak inflow rates, but the sustained nature of those rates over many hours had left no operational margin when minor variations or increased localized flow occurred. The concept of design capacity had referred to the system's ability to handle water at specified rates, but had not explicitly addressed how long those rates could be sustained before secondary effects such as soil saturation, storage depletion, and back pressure began to limit function. The event had not revealed a failure of infrastructure, but it had revealed a condition in which performance degraded not because limits were exceeded instantaneously, but because they were approached and held for longer than the system had been optimized to endure. Documentation of the event was compiled into an internal report that included rainfall data, infrastructure performance metrics, and comparisons to design standards. The report noted that total rainfall exceeded the 10-year storm threshold and approached the 15-year threshold for 24-hour accumulation, but that the distribution of that rainfall over 9 hours rather than a shorter period had created conditions not explicitly modeled in the design process.
It observed that drainage recovery times had extended beyond typical post-storm intervals, and that standing water had persisted in some areas for 8 to 12 hours after precipitation ended. The report cataloged pump station run times, retention pond high water marks, and locations where streets had retained water into the evening hours. It referenced city drainage design manuals, Florida Department of Transportation stormwater criteria, and Southwest Florida Water Management District regulations, noting that existing standards addressed intensity and volume but provided less specific guidance on system behavior during prolonged moderate-intensity events. The document was filed with the city's Public Works Department and made available to engineers involved in future infrastructure planning and capital improvement projects. No recommendations were included in the initial report. No operational changes were mandated. The event was recorded as a condition in which the stormwater system had operated within its functional parameters while nonetheless producing drainage delays that extended through the majority of a working day and into the evening hours across multiple areas of the city.